Hello, my name is Tejas Karmarkar from Microsoft. I'm a senior program manager in Azure Big Compute. So I want to talk about how you can use Microsoft Azure to do simulation and engineering work. For example, car crash simulation, as you see here on the screen. So I'll be talking about that um, and capabilities of Microsoft Azure. So obviously we're at a supercomputing conference, so I don't need to talk a whole lot on why HPC is important, but the critical piece is for automotive or manufacturing industry, the critical piece is how you shorten the product development cycle. That's why people use HPC for to run simulations faster so they can make better design decisions. And value proposition for HPC in the cloud is, as I said, um, traditional model has been that you buy large number of servers and create compute clusters on-prem, but it's always a step function. You can't keep adding capacity, which can match your flexible usage. So, traditional model has been a physical hardware, and the cloud model really, changes that instead of capex to opex, and give you flexibility of to use cloud when you need it. So that's a big advantage of doing it in the cloud. So in discrete manufacturing industry, you talk about aerospace, automotive, consumer product goods. In this type of industry, finite element analysis is one of the primary drivers of doing high performance computing. Computational fluid dynamics, multi-body analysis, as well as we see a significant usage in electronic design automation as well, where customers are designing silicon parts basically or chips. Tremendous amount of compute is done in that space as well. So we're trying to address kind of all these markets in a manufacturing space. As I said, today's infrastructure on-prem, which is great. A lot of companies do that, but I call it kind of a monolithic cluster. It means you buy 100 servers, you create a cluster. It's 100 servers and so many thousands of CPUs. Tomorrow, if you need 5,000 more, you have to order more hardware, wait for months for hardware to be delivered. Then it comes on site, you configure. There is no flexibility in it. And that flexibility can be provided by the cloud. And we think that that's not enough compute power for really engineers and scientists. They always want more compute, they want more storage, and anything you buy on-prem is never enough. And for example, if you're a car company, your CIO will come in at some point and come and ask, are we a car company or we are a supercomputing company? So that's why cloud becomes really viable. My background is automotive. I've been in Detroit for 17 years, used to run simulations myself. And this is a typical design workflow you will see a simulation or a CA engineer follow. You get a design from a CAD engineer where either you're designing seats or cars or bumpers. A CA engineer will take this design, create a mesh, apply boundary conditions, and will actually run simulation. And they keep doing this kind of workflow for every simulation that they run. And obviously they're trying to predict what kind of failures there will be in a model. But really, when simulation engineers do that, they're really trying to validate if the design is good or not. They're not really trying to drive the design, right? So take an example of a car crash simulation. It's a highly nonlinear event. You crash the same car 4 times, you'll get 4 different results because it's a nonlinear event. Material is nonlinear, geometry is nonlinear. The event itself is so fast and nonlinear, very difficult to predict. So in order to drive the design, you need a statistical baseline. So how can I get a statistical baseline? I have to do lots of runs. I have to run the simulation again and again multiple times so I can at least have some predictable baseline, and I can say, go and change the thickness of your crash box in your rails or in your engine mounts, or change the foam in your bumper design, examples like that. And today's compute power, I talked to a lot of automotive OEMs, they don't have enough compute power to run their day-to-day simulations, forget about doing optimization or statistical analysis, you're going to need like thousands and thousands of more cores. So cloud becomes really viable to do design of experiments optimization rather than doing your day-to-day compute. What we do in Azure is, imagine this process being repeated thousands of times. Some of the car simulations that we see generate 30 gigs of data per simulation. If you run it 10,000 times, you're going to have a problem on your hand that you can't handle the data. And we can take care of that in Azure. We don't have a magic wand, but we have enough compute capacity and infrastructure. And we have a product called Azure Batch that takes care of some of these bottlenecks. So imagine running 1,000 simulations. You're going to have your scheduler create a queue which has now your wait time suddenly increased from 1 hour to 10 hours to 20 hours. Your jobs are sitting in the queue for a long time. Problem after you finish the job, how do you analyze the results? So we remove some of these bottlenecks that are created using Azure Batch. We go and provision thousands of cores for you. We do the automated data movement. We automatically can write scripts that will help you analyze the data as well. So some of these bottlenecks that you will see in doing design of experiments or in optimization, cloud really becomes a viable solution with the automation engine like Azure Batch. That's just fancy graphics there. So Microsoft Azure can provide on-demand infrastructure, can help engineers really drive optimal design. That's kind of the message or use cases that we see. So to address the engineer compute needs, we primarily have two products. One is called Big Compute, or that's traditional infrastructure as a service in Microsoft Azure, and then we have Azure Batch. Big Compute is your traditional infrastructure. We have QDR InfiniBand enabled compute nodes in Microsoft Azure, which are available to you per hour, per minute to use, and you pay for what you use. We have software-defined networking, so you can create your own network within Azure. So it's segregated. It's not a public cloud where everybody's email is floating around and things like that. Then it's isolated network virtually. So you control your own IP range. You define your own subnets and things like that. So you can have software-defined networking there. You can have connectivity to your on-prem infrastructure, so you can tap into your existing application license server and things like that, as well as it can follow the IP ranges that you use or the schemes that you use on-prem. We have an offering called ExpressRoute, which is MPLS connectivity through a secure channel or secure network with your ISP directly into Azure, or you can do VPN. We have different interfaces. So obviously we have a portal, a website. You can go and spin up these machines. We have a CLI interface that's available on Linux, Windows, or pretty much any platform of your choice. And we have different storage options. So we work very closely with Intel. We have a Lustre parallel file system available in Azure that can be used as a global scratch, as well as we have blob storage, which we recommend for long-term storage, page blob and disk blob. We support Intel MPI on Linux and Microsoft MPI on Windows. And we are working closely with IBM on platform MPI implementation, which will be available very soon. And the most important thing coming from Microsoft, we do Linux. And we do Linux for high-performance computing now through our Linux RDMA interface. So we launched Linux RDMA through SUSE Linux 12. CentOS is in private preview right now. And we recently announced our partnership with Red Hat. So we'll have Red Hat available pretty soon as well. So that's Big Compute. On the Azure Batch side, Azure Batch, think of it as like a automation engine built on top of Azure infrastructure. So it's not really stateless, but it appears as a stateless for the end user. You don't have to worry about operating system and an image. You want to provision 10,000 cores, you could tell Azure Batch, it goes provision 10,000 cores. It doesn't support MPI yet, so it's really good for embarrassingly parallel workloads. In future, we'll start supporting MPI. There is no operating system to maintain or operating system image to maintain. And it works at hyperscale. We have done testing up to 20,000 cores. So Azure Big Compute, here is a quick schematic that shows what customer is responsible for and what we are responsible for. So pretty much everything above the operating system level, scheduler application and visualization is customers responsible for. Rest of the infrastructure, we take care of that. We have 2 instances in Azure that are InfiniBand enabled with QDR InfiniBand. They are called A8 and A9. So A8 instance has a 56 gig of memory. A9 has 112 gig of memory. They are Intel E2670 SandyBridge processors. It's a very well-balanced system, so CPU is not waiting for interconnect to catch up. You'll see very good performance close to bare metal. And as I said, we have QDR InfiniBand dedicated only for MPI traffic. And then we have a front-end 10 gig network that's for the rest of Azure, for maintenance, for heartbeats, as well as for storage traffic is through the front-end network. We have G-series nodes. These are some of the biggest compute nodes in the cloud. We have a G10 that's about a half a terabyte of memory and 32 processors. We don't do hyper-threading. We have a turbo on, but we don't oversubscribe the machine. So if you have an A9, there's 16 physical cores on the box. You get all 16 physical cores, even if the machine is virtual. And the G-series nodes are really good for implicit workloads like Nastran, Abacus 2D. These applications require a lot of I/O. So the G-series has a half a terabyte of memory, so you can obviously utilize that memory if you want to do shared memory parallel, something like that on the local node. And it has solid state drives. So you have terabytes and terabytes of local scratch that can be used for high I/O applications. And then we have A10, A11 nodes that are same processor as A8, A9, but without InfiniBand. So if you want a high frequency processor. This process is getting a little old, so we are working on next generation, which we'll announce early next year. It's a little bit of an eye chart, but kind of architecture. If you want to set up a fairly large cluster in Azure with Lustre parallel file system, as you can see here, you can connect to the cloud through express route or a VPN. And then we have a dedicated backend network for MPI, and the front-end network really talks to the Lustre parallel file system or your web portal, or if you're working with Cycle computing will interact through that front-end 10 gig network, and the backend network is dedicated for MPI only. That's really important because through our MPI implementation or RDMA implementation, we get 2.5 to 3 microsecond latency and about 3.2 to 3.5 Gbps bandwidth, which is really critical when your number of cores for MPI job starts increasing. So if you're running a 32, 64 core job, no problem, right? You can run it on Ethernet. But we have a customers running 1600 core jobs, true MPI jobs, parallelized through MPI. That's where this kind of latency will kick in. And even one microsecond increase in latency can have a dramatic effect on MPI jobs. So that's what we have here with a dedicated backend network. We can really offer you low latency, even with switch ops and everything included, that can run your jobs really fast and show you linear scaling at large core counts. So as I said, you can use the G-series for linear static and topology optimization, those kind of workloads. You can use G-series. And for true MPI type applications like crash simulation or computational fluid dynamics, you can use A8, A9. I want to skip through Azure Batch a little bit because it doesn't support MPI yet. But think of Azure Batch as an abstraction layer above cloud or above infrastructure as a service. So it's a fully automated engine available through APIs that will do automated provisioning, automated data movement, and automated job scheduling. It's really designed for ISVs that want to offer infrastructure, that want to offer software as a service, or if you want to create an integration, is available through APIs, and it's really abstracted above, as I said, infrastructure. We are coming from Microsoft. We obviously understand the importance of big compute or HPC ecosystem. I kind of tend to use the big compute name because as soon as I say HPC, people think it's rocket science, and we want to make HPC more mainstream, so we call it big compute. So we work with all the standard ISVs. We work closely with Altair, LSTC, Ansys, Simulia, Plus, we work with different Linux distros as well. As you can see, CentOS and SUSE Linux. And the Red Hat we literally announced, I think, 3 weeks ago. So Red Hat would go up there too. We work closely with obviously Cycle Computing and as well as Mellanox and some of the hardware providers as well. So all these technologies kind of, we think, enables 4 major scenarios, right? It's large enterprise customers, like I said, car companies of the world, that want to set up a dedicated cloud in Azure. So here's a quick schematic on that, where you have a head node into the Azure cloud, and you have all the compute being done in the cloud, and you're connecting to on-prem and submitting jobs from on-prem. That's one scenario. The second scenario is hybrid, which is also very popular because a lot of customers have existing infrastructure. They can't just throw that away. So, but they need a capacity from time to time. That's where cycle computing kind of comes in and gives you that flexibility to run more compute in the Azure. So the same head node will ship jobs to the cloud and run it in the cloud. The third scenario, which we see popular, that's where again cycle computing kind of plays in, is creating software as a service offering from ISVs. For example, I believe Ansys has their enterprise cloud enabled, that they offer software as a service. Altair, there are a lot of companies that offer similar services. So you can go to a website and run a simulation. You don't have to buy licenses, you're paying for licenses by an hour. And our system in Azure is available through APIs, so it enables the SaaS type scenario, along with our partnership with Cycle. And then we have a marketplace. Think of this as like an app marketplace for cloud. And our marketplace is across hundreds of countries around the world. It takes the burden of commerce out of ISV, that they don't have to worry about the distribution channel, they don't have to worry about reaching small customers, whether it's a student in a university or a researcher or a small consulting organization. They can come to Azure, they can deploy compute nodes, they can run simulation and pay for every minute that they use. So today we have some offerings in the marketplace from a company called Uber Cloud that has enabled MPI applications through implementation of Docker. So it's a very, very interesting technology, and it's a one-click deployment of the entire compute cluster in Azure through our marketplace. The important thing, you pay for what you use. Here's a different workload, as I said, top scenarios that we see in automotive industry, industrial design, rendering, design engineering, which is, as well as marketing. So rendering plays a big role in creating marketing images. That requires significant amount of compute. So we see usage of A8, A9 instances for this type of scenarios. And at the end, I want to kind of quickly wrap up with my Microsoft, right? So a lot of people don't know the scale at which we operate. We're obviously enterprise grade, which is the largest enterprise software company in the world. We understand what enterprises need. So a lot of our large customers come to us and say, we want to do compute in the cloud, please help us. We have data centers around the world. Our one data center, one region is the size of 17 football fields. So we buy significant amount of servers in the world. We buy petabytes and petabytes of storage. We announced 3 regions recently in India. They're live now. So we just continue to increase. We have announced recently that we're going to build a data center in Germany as well. So we continue to invest about $6 billion. It's publicly available figure through our earnings report. We invest about $6 billion per year in cloud infrastructure. And we are bringing that to the market to the benefit of our customers. And we just continue to invest. A lot of people don't know, but we have 3rd or 4th largest private network in the world connected by dark fiber. So when you're moving data across our data centers, it's moving across our own dark fiber. So, and when we're doing innovation in the cloud space, we do, this is one of our Gen 4 data center looks like. We do innovation from literally from motherboard to the cooling and the thermal systems, and can we use ambient air, and we have literally millions and millions of servers in these data centers. And here is a data center where the servers come in a container, literally on a truck, and they get docked in our data center. You connect cooling and electricity and network, and you're in business. One of these containers has about 3,000 physical servers. So we take cloud very seriously, and we're investing a tremendous amount of capital to bring these cloud capabilities for our customers. So with that, I kind of end my talk, and will be open to any questions anybody has. Thank you.